Hey guys, you're watching Python tutorials on my YouTube channel, Python for Microscopists. Again, you'll soon realize that this is not just for microscopists, this is for anyone interested in data or image analysis. Now, until now, I covered traditional machine learning and quite a bit of deep learning, but in this video, I'd like to combine best of the both worlds to create a solution that works amazingly well, especially when you have limited training data. Now, you probably have seen a plot something like this. I'm not sure how accurate this is. This is just, again, I should say just it looks like, a hand-drawn plot, but there is some reality to this, which is if you have loads of training data, deep learning works great, yeah, compared to traditional machine learning. If you have very limited training data, meaning you have only tens of images rather than thousands of images, then the traditional machine learning works great. When I say traditional machine learning, this is random forest and support vector machines and something of this sort, okay? Now, with traditional machine learning, we extract features and then use random forest. Please watch my video 67 and 67b on this specific topic where we extracted features and used random forest for image. In that example, it was semantic segmentation, but even for classification, the approach would be the same. So let's actually go ahead and in this video, take the best of the both worlds, meaning from the deep learning world, instead of doing the deep learning, let's only take the convolutional filters and extract features using the convolutional filters and then take that response as our features that go into random forest for classification. So in this video, let's look at classification. In the next video, let's look at semantic segmentation. But what I'm talking about is you have, for example, a model that looks very similar to this. You have a few convolutional layers, max pooling layer, batch normalization, convolutional, max pooling layers, and so on. As you get down here, now we connect them to fully connected or dense layers with an output layer predicting or the outcome. So what we are going to do is chop part of this off and then only take some convolutional layers and add our random forest as a classifier so we can do classification or regression or semantic segmentation. So in this tutorial, again, as I said, let's look at the classification problem. So let's jump directly into the code. And before looking at the code, I want to show you what images we are working with. So here I downloaded a bunch of images from Google. They come with I'm pretty sure they come with some sort of copyright law, so I'm not going to distribute them. You can download your own images for this type of exercise. So I'm not going to share any images, but I downloaded about 78 images, 78, that's it. Definitely not enough for deep learning, and you'll get crappy results, and we'll see that in a minute, okay? But 78 images for barn, about 80 images, again, 74 images for dog park, and about 80 images for landscape, and sunset. I did 86 images for sunset. So these are the images we're going to use, and you'll know that right away. These are not anyway close to what you need for deep learning, but with traditional machine learning, they actually are, you'll see acceptable results. Now, if you look at dog park, I expect higher uncertainty with dog park because most of these images either overlap with natural landscapes or barn. You see, some of these images overlap with landscape and some overlap with barn. And also in the barn, you have images like this that can be confusing. So I'm not sure what type of accuracy we'll get. Literally, I just downloaded this and I'm doing this video because we'll see. Why not live on the edge? Okay, so this is what we have. Now let's jump into the code. And the code should be pretty straightforward. We are going to import the standard libraries for handling data like NumPy, Matplotlib, glob for walking through the folder structure and reading the images, and CV2 OpenCV for reading images. So let's run these lines. And then from Keras, we don't need much. We need model, sequential, dense. I'm not even sure if I'm using flatten. Obviously, looks like I am. But let's import the standard libraries and Seaborn for plotting. Maybe I don't need pyplot. Okay, so now let's just look at, I dumped all my images into a folder called natural. Earlier I had another folder where I was testing malarial cell images. That's where I tested. I did not test it on natural. We'll see. Anyway, so malarial, where we looked at parasitized and unparasitized or uninfected images. Now let's look at 4 classes. I thought 4 is better than binary classification, so why not do this? Okay, so let's go ahead and walk through this to see what we have. So it automatically realized, okay, we have train and validation data sets. I'm not even sure if I'm separating. Yeah, looks like I'm separating validation. Sorry if it sounds like I'm not prepared for this video, but we'll see. Okay, so these are the 2 folders that we are walking through, and let's leave the size to 128. The size here, I'm defining it so we can resize the images. The deep learning part doesn't work well with larger images, right? I mean, I could have worked with 512 by 512, but deep learning part, it's pretty memory intensive. So let's resize all images to 128. I think it should prove the point. So that's the size I'm defining. And then I'm actually walking through the folder, train folder, okay, where it looks at each folder name, and then it assigns the folder name as label. All I'm doing is looking at the entire directory path, and I'm splitting at where it's separated. Again, 2 forward slashes because this is Windows system, or if you're working on a Linux or other system, maybe it's just 1 regular slash, okay? But again, if you see an error here, change it and play with it. Okay, so my label is going to be the name of the folder itself. So in this case, we have barn, dog park, and so on. And after that, I'm just walking through each image and reading the images and converting them from RGB to BGR. I don't think you even need this. I just included that. And then I'm going to append that to the empty list I opened here. Same with both images and labels. Okay, I hope this is not too confusing for you guys. We have done this a few times in the past. Okay. So there you go, it's walking through every image, and if you look at your train images, there should be 320 images right there. And if I open this, you should see all the NumPy arrays for each of these image. And then the train labels should be the first 72 should be barn, and then comes dog park, and then comes landscape, and so on. So basically for each image, what is the corresponding label? We do exactly the same. Now, so far, this is just a list, right? We cannot work with list. Well, you can, but you have to go through the for loop to go through each element of the list. Let's actually work with NumPy arrays because it makes our life easy. So we are converting our lists into NumPy array. Again, I apologize if you think I'm explaining too basic stuff, but you never know who's watching the videos. Okay, so test. I'm doing exactly the same thing I did for train images with the test images. That's pretty much it. Okay, so eventually at the end of this, I'll have train images, train labels, test images, test labels. Okay, now what? Now our labels, you just saw that our labels are all barn, dog park, and landscape. This doesn't work well with deep learning or any machine learning, so we have to convert them into some sort of a number. So for that, I use scikit-learn's pre-processing. And within pre-processing, you have something called label encoder. This is amazing because you can encode, you can also decode at the end of it, okay, which we'll do. So I'm going to fit it with test labels and train, and I'm going to encode this. So again, I'll share the code so I don't have to go through every line in very detail. But if I look at train labels encoded, there you go. Now instead of barn, it's 0. Instead of dog park, it's 1, and the next one is 2, and the last sunset is 3. Okay, so this is how these are test. If you look at train, we should have 70 or something. Okay, oh yeah, we have a lot more. So now that's all great. Now I'm going to reassign the names. Typically you have like this humongous data set and you split it into X train, Y train, X test, Y test. I'm not splitting anything here. I'm just reassigning my train images into a name called X train. So it's easy for us to think about it. Okay, otherwise the naming would not make sense. So let's go ahead and do that. So now I have my X train, Y train, X test, and Y test. Okay, let's slowly go to the next level. Okay, so all of these values, they're all images, 8-bit. So the values go from 0 to 255. I am dividing each pixel value by 255. So my values range between 0 to 1. So in a way, I'm normalizing. Okay, well, normalizing is the wrong term. Normalize means you'll get a normal distribution. I'm scaling my values to between 0 and 1. So let's go ahead and do that. Okay, now if you look at your X train down here, you see it's float 64. and it's not integer anymore. So far so good. Now for deep learning, you need to work with, especially for these type of categorical labels, you have to convert the labels into one-hot encoding. What do I mean by that? Hopefully you watched my tutorial about one-hot encoding. If not, let's quickly look at our y-test. This is all 0 labels. These are all 1 labels. These are all 2 and 3. This is not how deep learning actually works. You convert them into one-hot, and let's look at the results so it's easy for me to explain. So remember, the first 4 or 5 data points had a value of 0. You see, that's what it says. So for each value, it's creating an entire column, and then the first 5 are zeros, next 5s are ones, the next are ones. So that's why it's called one-hot encoding, because in a given row, only 1 pixel is going to have a value of 1, and that's what the label is. Okay, a quick tutorial on one-hot encoding there. We're all set. Now comes the deep learning part. Okay, so you can import an existing architecture like VGG16 or AlexNet or some other network, ResNet, and then say, okay, I only want the first 2 convolutional layers, but I'm not going to do that. I'm going to define my own. You can experiment the other way. Okay, I'm going to define my own, architecture, which I do in every video. So here I'm saying, okay, let's separate this. Activation equals to sigmoid, that's fine. So instead of model equals to sequential, typically if you watch my previous videos, we do model equals to sequential and then model.add convolutional, model.add batch normalization, and so on. I'm going to separate my model part from this other part. You can still give it a name model. It doesn't matter. It's just a name. So in this case, the name I gave it is feature extractor. Okay. So equals to sequential, and to that I'm going to add convolutional layer 2D with 32 filters. Okay, 32 filters, and then another convolutional layer 32 filters, another convolutional layer 64, another convolutional 64. Okay, this is very similar to how we do our regular deep learning. In fact, that's exactly what we are seeing here. And then you flatten it, right? I mean, otherwise you have a dimension of 64. When you flatten it, it becomes 1 column. Again, this is how it goes into your dense layers. This is how it goes into your random forest, a column. It's not 2-dimensional, it's not multi-dimensional, okay? So that's why flattening is very important. So up to here, I called it feature extractor. Done. Next what? Next, I want to do deep learning. So for deep learning, let's take the feature extractor and let's add the final dense layers. How do we do that? Well, I assign a variable called x. To that, I add feature extractor dot output. So whatever that output is from feature extractor, it's nothing but our x. To that x, now I want to apply our dense, okay, with 128 dimension, and you see it's applying it on this x. Okay, so now I'm not using sequential and dot add. I'm using the old way of doing things, which is, okay, my x is nothing but the dense and then applied on x. This is my new x. Okay, now finally the output layer or prediction layer, if you want to call it, equals to dense 4. Why 4? Because I have 4 classes, right? I have 4 classes here, 1, 2, 3, 4. So depending on how many classes you have, of course, that's the number you're going to put down here. And again, this is a classification, multi-class classification problem. So our activation needs to be softmax, okay? And applied onto this X. And this is our prediction layer, okay? I hope you're following. And finally, our CNN model, right now I can call it model equals to, but since I have CNN and random forest, I just gave a different name. That's it. Is basically the model with inputs as feature extractor input, whatever this input is that goes into feature extractor, and my output is the prediction layer. So that's my model. Okay. And finally, I want to compile it using optimizer RMS prop and loss categorical cross entropy, and I'm going to track the metrics accuracy. This is exactly same as how we do when we define a regular neural network model, and finally I'm going to print the summary. If this is just a normal neural network problem right from the beginning, I would have just added model equals to sequential, model.add, 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 and all the way model.add, and also model.add dense 128 and model.add dense 4 and model.compile and model summary, right? I hope you know what I'm talking about. So let's okay, so we did not run these lines, so let's go ahead and do it, and you'll see that the output looks exactly same as before. Okay, what goes in is an image that has dimensions 128 by 128 by 3. What comes out is one of the 4 values, right? I mean 4 values coming out, and because we are using softmax, I believe if you sum all of these 4 values, it should be equal to 1. Okay, so that's how the model is. Again, so far we are not doing anything when it comes to random forest. This is completely neural networks. I just showed you a different way of defining your model. Okay, now let's go ahead and train it. This part you should know already, right? I mean, model.fit or train, and y values is y train 1 hot. We just did 1 hot encoding. And for 50 epochs, this should be relatively fast because we don't have a lot of data. That's the whole point here. And validation, let's use x test and y test 1 hot. Okay, let's go ahead and run this, and let's see how fast this actually works. Let's see, it's firing up, so that's not bad. Okay, let me pause this video for a few seconds, and once it's done, I'll continue this. Okay, so even with GPU of 4 GB, it actually took 4 minutes, so that's a bit long, I should say. Anyway, so now that the training is done, let's have a quick look at the loss and the accuracy curves. So if you look at the loss curves, obviously it's jumping up and down. Again, in 3-4 videos ago, I talked about the loss curves and validation and training loss and how to interpret them. And as you can clearly see, this is a case where the training data is doing pretty good, and the actual testing data is not doing good. It's jumping all over the place because the testing data apparently is not representative of what training is trying to do. Okay, but we know that we only have like 5 images each of each class in this case, so we don't have a lot of training testing data for validation. That's fine. So let's just look at the accuracy. I think we'll get decent accuracy. I mean, not close to 80-90%, but on the test we have about 60 to 65%. Sometimes it's jumping up to 70% or so, but we'll test it out in a minute anyway. Okay, so this is just initial estimation. Now let's go ahead and predict it. Now, if you want to predict it, all you got to do is, obviously we know this, right? I mean, CNN model.predict, predict on what? Predict on X test, right? So let's go ahead and do that. And if you look at the prediction neural network, you can see that the predictions are all 1 hot encoded. That means we need to get them back to the actual labels. And you can see the values, I believe if you add 0 plus 1 plus 2 plus 3 in this case, they all add to 1. But here, for this image, it makes sense that, okay, this has a probability of 83% or 84%. Everything else is very low. So probably the label is 0. So how do we get the labels back to original? argmax, okay? numpy.argmax. Apply this to prediction. Don't forget to put axis equals to -1, otherwise you'll just have like 1 value. At the end of it, again, test it out. So now if I open prediction, now you can see, okay, 0, 0, 2, and so on. It's basically taking the maximum and giving us the value right there. Okay, now we also did some transformation here, right? We went from barn and sunset to 0, 1, 2, 3. So how do we get those back? Again, if you remember, we encoded them and assigned it to a variable called LE, if I can find it, right there, LE. So I can use exactly the same to do the reverse transformation. So to do that, it's basically inverse transform. So let's go ahead and do it. And our prediction NN now will be barn, landscape, barn, and so on. I hope you're learning something here. Okay, again, I hope you don't find this to be boring where I'm repeating stuff that you already know. Again, reinforcement is not a bad thing. Okay, now let's go ahead and why did I do all of that exercise? I just want to do a confusion matrix to get a nice heat map of how things are going here for each class. Okay, so if you look at that, for this first class, out of 5 images, it got 3 correct. The next one, oh, I'm pretty surprised that it actually did okay with this second class, and the third class, 2 correct, and the last one 5 correct. So overall, it's not as bad as I thought. Okay. So that's your and we can also predict on one single image, right? So let's actually select an image n equals to 5. Again, I'm curious about dog park, so let's go ahead and do that, and let's plot that image from the test, and there you go. That's the dog park. Okay. Now, how does it actually predict? And again, I'm not going to explain each of this line. You can see that, oh, dog park is doing pretty good. I take my word back. So neural networks are not as bad as I thought, even with limited training data. Okay, but let's see how random forest actually does. So in this case, the overall accuracy we ended up with is 65% at the end of this training, as you can see. Now, if we get anything better than 65% with random forest, I can claim that I wasn't wrong to begin with, and I like to be right. Okay. So now let's use the features from convolutional. Now there is a reason why we defined this as feature extractor, because now I want to apply this feature extractor onto our input images and extract only the features, not this entire thing. So you know what I'm trying to do. Instead of running CNN model like we did here, CNN model.fit, I want to do feature extractor.fit. So the output would be just our feed forward convolutional neural network result. Okay, so let's do that. So for that, I'm assigning a variable called x for random forest feature extractor dot predict on what? On my x train. So when I do that, it should take a second. And then there you go. Now I should have, if I can find it, x for random forest, 320 images, right? And then 65,536. That's the size. Why is it one dimension? That's because as part of feature extractor, we included the flatten. Okay, that's why it's not 64 or anything. It's flatten, it's one column. Okay, now that we have our X ready, we are all set to train the model. So let's go ahead and import our random forest from scikit-learn ensemble. Let's put 50 trees for now. That should be fine. Let's go ahead and define random forest. We are not fitting it yet. Now let's go ahead and fit. Now for random forest, it doesn't work with one hot encoded data. It works with one column of data, which is Y train. What is our Y train? There you go. All zeros, ones, twos, threes, and fours. Okay. So this is how random forest works. That's why let's go ahead and use it. Let's fit it. Super fast. This is how fast random forest is. So literally maybe 3 seconds or so, okay? Compared to neural networks, which took 4 minutes. And neural network, 4 minutes on GPU. This random forest is just CPU. So this is a bit faster. Okay, now let's send the data through the same feature extractor process. Now I want to predict, right, onto my test dataset. But my test dataset, I need to extract the same features. Remember, if you watched video 67, we extracted a bunch of features from training images. The same features need to be extracted from testing images because those are the values we're trying to fit. So here, xtest feature. Let's go ahead and do that. And now my prediction is my random forest model that we just trained on, dot predict, and the xtest feature that we just got here. Okay, sorry. I shouldn't have selected. Let's go ahead and run this line again. Okay, so my prediction is here, and let's go ahead and look at the prediction random forest. So here is my prediction. Okay, this is not one hot encoded, so I don't need to do any tricks, but I need to convert them into my barn and actual labels. So for that, we know how to do that. LE inverse transform. So we have this. So let's look at the accuracy right here, and the accuracy is 75%. Much, well, a little bit better, not much, but better than neural networks. Okay. So now let's go ahead and print the confusion matrix and see how this looks like. This is not bad actually for the second class, which I thought was the difficult one. Apparently that is the easy one. I'm not surprised that all 5 of these sunset are correctly classified. That's because sunset images, they have a lot of color, bright color, and I think it uses one of the filters, could be the one that actually highlights this color, and also the sun appear to be in the saturated color, so that also helps. But yeah, overall that's not bad. In fact, the barn is the one that actually got low accuracy. Fine, let's go ahead and have a quick look at how this image got classified. The same image, and the same image here, dog park, is classified as dog park. For the fun of it, let's just select something else. I don't know, let's do image 17. No, well, it must be one of the final images, right? Sunset, this should be correctly identified. Let's actually do image 12 and see how that does. That looks so synthetic. It says sunset, the actual label is landscape. To me, it fits more like a sunset than landscape. I think Random Forest is doing a better job than whoever classified that as landscape. So let's do one more. Label 9. And what is that? Dog park and dog park. And label 9 with our traditional neural network. Let's go ahead and do label 9. And let's see how it does it. Right there, dog park. I think we built an amazing classifier right here, both random forest and neural networks, but you got the point here. So go ahead and try this on your own images. This can be a very useful approach. In the past, I used this approach to classify texture of a whole bunch of minerals, so there were a lot of light microscopy images of different minerals. And well, the chemistry is the same, but the mineralogy, the mineralogy is the same, but the texture is different between these different minerals. So I used this very similar approach to actually separate them into different classes. And in that case, it was like 12 different classes or so, and it actually worked very, very well. So whether it is geology, material science, or life sciences, this can be a great approach for classification. Keep watching, because in the next tutorial, I'm going to talk about exactly the same approach, but for pixel classification, which means semantic segmentation. Okay, so thank you very much, and I hope you found this tutorial to be useful. If you haven't already subscribed to this channel, what are you waiting for? Please go ahead and subscribe. Thank you very much.